maybe? Okay. So today we're going to take a look at section 5.3. It's called the binomial distribution. We have been working with probability distributions for discrete random variables. We've made them in table form. We've graphed them. We found mean, variance, and standard deviation. We did all those things. Now we're going to look at a more specific type of distribution, probability distribution for discrete random variable. A little more specific type. And we'll do a few more specific types next week. So a binomial experiment is a probability experiment that satisfies the following conditions. And I apologize, I didn't fill in that bullet point on your sheet. I don't know why. I got a little delete happy, I guess. So it's kind of up to you if you want to write that piece or not, or if you just want to go ahead and write the 4 conditions. It's kind of up to you. Now these conditions, the list we're going to make, I talked about we're going to look at some other distributions next week. The list we're going to make is going to be your little mental checklist when you get on your test or your review, you're preparing for your test. It's going to be your little mental checklist of, okay, this is when I use the binomial distribution. This is when I use it. It's going to be your checklist. It's how you're going to know to choose binomial over one of the others that we do next week. So condition number 1, there must be a fixed number of trials. So it has to be set out from the very beginning. I'm going to flip the coin 17 times. I'm going to draw 5 cards from the deck of cards. I'm going to select 8 students. Has to be a fixed number of trials that has to be set out in advance. Property number 2. It's the longest one to write, I promise. Each trial can only have 2 outcomes, or outcomes that you can reduce down so they fit into just 2 outcomes, 2 different groups. The outcomes will either be considered a success or a failure. There's nothing in between. It's either a success or a failure, nothing in between. All right, so think about the prefix bi. Think about a bicycle only having 2 wheels. A binomial in math only has 2 terms. So our binomial experiment can only have 2 outcomes. It can only have 2 outcomes, either success or a failure. All right, for our third property, the outcomes of each trial must be independent of each other. We talked about independent and dependent events last unit quite a bit when we were figuring out our multiplication rules for probability. What that essentially means is, just a refresher, that the fact that trial 1 happens cannot affect the probability of trial 2, or trial 3, or trial 4. Or trial number 2 cannot affect the probability that trial 3 is a success. So all the outcomes must be independent of each other. And then along the same lines, I always think 3 and 4, they really just fit right together. The probability of success has to be the same for each trial. So if I'm looking at drawing a red card from the deck of cards, I'm going to draw 5 cards out. When I draw my first card out, the probability that I get a red card is a half. The probability that I get a red card for my second draw has to still be a half, or my third draw, my fourth draw. It has to stay the same for every trial. My probability cannot change. Now, if these 4 conditions are met, when we create our probability distribution, it is called a binomial distribution. So remember, our probability distributions, they had our outcomes and the corresponding probabilities. Same idea here, we're just putting that specific name on it. If these 4 properties are met, we have a specific type of experiment, we have a specific type of distribution. So this is the checklist that you're going to want to go through when you come across a question on your test or your review for the test. And even as you're doing your practice problems, I know that all the practice problems for this section are going to go right with these 4 steps. But as you're doing that practice, do that checklist. Here's why I'm doing what I'm doing. These 4 steps are met. Here's how they are met. Do that for each situation you come across. So that way when it comes time to review for your test, and it comes time for the test, you're a little bit more confident that, yep, I'm familiar with those 4 steps. I can pick out a binomial distribution really easily. So let's just take a look at one example and just focus on going through the checklist. So not worrying about any kind of formulas, probabilities, anything like that. Let's just look at the checklist. All right, so here's our first situation. A coin is tossed 4 times. Find the probability of getting exactly 2 heads. How we saw this in the past, we would have created a sample space. Maybe you made a tree diagram first. Now for some of you, like, no, Miss Callie, don't start talking tree diagrams. Some of you might have created a tree diagram first, and then you would have listed out your sample space. Head, 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 tail, etc., etc. That can take a while. That can take a while, especially the more and more trials that you have. So let's see if this could possibly fit the binomial experiment. Property number 1 says we need a fixed number of trials. Done. We have 4. Now, to save you a little bit of writing, if you want to, you could just draw an arrow over to your property on the left and just put that we have 4 trials. Property number 1 is met because there's 4 trials. It's fixed. It's done. So if you don't want to rewrite that whole first property, totally fine. I would just maybe draw a little arrow over. Hey, this is the one that we're meeting right now. Fixed number of trials, check. There's 4. Property number 2 says we need 2 outcomes. Again, maybe you just draw an arrow over to that left side, and then you just put that you have heads, tails. 2 outcomes. That's it. Again, if you want to rewrite, you can, but save a little bit of pencil lead here. So we only have 2 outcomes, and that is all. That's all we can have for binomial. All right, property number 3 says our trials need to be independent of each other. So the outcomes are independent. That's what property 3 says. The outcome of one toss does not affect the outcome of another toss. If you need to write that down, or if you feel really comfortable with the idea of independent events, then I would just put the outcomes are independent. Or if you want to write the piece I've underlined, it's kind of up to you what you need. This is your checklist. And again, I really want to stress this piece. This is going to become a mental checklist for you. I'm not going to have the expectation that you are writing this out every time. This is going to be that mental checklist of, is this actually a binomial experiment? All right, then last but not least, number 4, the probability of success has to stay the same for each toss. And in this case, heads is 1/2 in each case or each trial. or you can rewrite the whole thing. It's kind of up to you. So our checklist, it looks good. All 4 things are met. They're pretty simple things to check for. But as you're doing your practice, keep going with that mental checklist just so it becomes like second nature to you. So when it comes time for the test, you're not trying to memorize this and cram it in. You already know it because you've been working with it when you did your practice and then again when you review for your test. All right, so now what does this mean for us? How does this get rid of having to create that whole sample space just to find some probabilities? So here's what we can do. Since we want exactly 2 heads, heads are considered a success in this case, and 2 tails, a tail in this case would be a failure. I know sometimes we have to kind of wrap our head around it, like, well, why do we consider that a success and failure? That's just our verbiage, for lack of better wording, for this particular type of experiment. So we want exactly 2 heads and 2 tails. So here's what a lot of you tried to do in chapter 4. Sky, can't I just multiply that together? Can't it just be a half times a half times a half times a half? Doesn't that give me what I need? Well, if we were to look, if we actually made a tree for this and we stop and think about it, there's going to be 16 outcomes. So we're tossing the coin 4 times. So it's going to be 2 outcomes on the first toss, 2 on the second, 2 on the third, 2 on the fourth. Multiply all those 2s, we're going to get 16 total outcomes. If I just say my probability is 1/16, that means it only happens 1 out of 16 times that I get 2 heads and 2 tails. No, that's not quite right. It's going to happen more than that I get 2 heads and 2 tails. So if we just multiply those probabilities together, here's what's not taken into consideration. If we were to actually draw out the tree and create that sample space, we would see all the things we have to consider. The 2 heads could be the first and second toss. It could be the first and third. It could be the second and fourth. It could be second and third. Any of those situations will work. So we have to figure out how many times 2 heads actually occurs. How many ways? How many ways? If I have 4 coins, how many ways can I have it of selecting 2 of them to be heads? So this links us back to our combinations from last unit. The order doesn't matter. That's why it's a combination. I'm looking at 4 tosses. I need to select 2 of them to be heads. I have 4 tosses. I just need to select 2 of them to be heads. It doesn't matter if the heads are on the first and second, first and third. That doesn't matter. I need 2 of them to be heads. So what that looks like is 4 tosses of the coin. I want 2 of them to be heads. So what this gives me, without having to draw the tree diagram, this tells me how many of those 16 outcomes in that sample space, or the 16 branches of our tree, it tells me how many of them are going to contain 2 heads. It tells me how many are going to contain 2 heads. What's that?
Do we need all the word with the 4 exclamation mark?
No, you guys wouldn't need this work. I'm just showing you how it fits. So the question was, do we have to show all that? Nope. We did some awesome calculator shortcuts with those combinations, and those absolutely still apply. All right, so let's put the 2 together. The 6 tells me how many ways I can get 2 heads out of the 4 tosses. And then that 1/16, that 16 is giving me my total outcomes. So 6 total ways it can happen, disregarding order. How many ways can it happen? And then that 16 gives me my total number of ways. That's how many items would be in our sample space. That's how many branches would be on our tree. So yes, instead of having to draw out that giant sample space, create a tree, yes, we can use the idea of combinations. with a little bit of our multiplication rule. Mixing those two together because the 4 conditions have been met. The 4 conditions of our binomial experiment have been met. So let's actually summarize this into a nice formula for us. Bottom right-hand corner of your sheet gives us that formula piece. But what I want to show you, though, this first part right here, guys, that's just our NCR. So if you want to go ahead and shortcut that, you sure can. And to be honest, for our purposes, I'm going to be very honest, this P of S thing, it's not appearing in that formula. So let's try to condense this down a little bit. Don't worry about those. That notation isn't in our formula anywhere. Let's worry about the things that are. Let's try to cut that out a little bit. So the P, the little p, lowercase p, is the numerical probability of success. Q is the numerical probability of failure. Remember, those are our only choices. There's nothing in between. Either we get heads on the coin or we don't. We draw a red card from the deck or we don't. We roll doubles on the dice or we don't. So if I have P and Q, if I add P and Q together, I get 1. Because it's either a success or a failure. There's nothing else in between. N is our total number of trials. So how many times are you flipping the coin? How many students are being selected? How many times are we drawing a card from the deck? N's your total number of trials. And then the capital X is how many successes you want. We wanted 2 heads. Maybe I'm drawing a card from a deck 6 times. Maybe I want 2 of them to be diamonds. How many successes do you want? The little inequality down at the bottom is just showing us that our number of successes, it could be 0, but we have to make sure that we don't go beyond our number of trials. So if I only have 6 trials, I can't have 7 successes. It won't work. I'm out of trials to have those successes on. So let's put this into action. Let's do a couple examples, and then we'll finish up today talking about the mean, variance, and standard deviation for this particular type of distribution. All right, so we have 90% of graduates of State University who apply to a particular medical school are admitted. This year, 6 graduates from State University have applied for admission to medical school. Find the probability that only 4 will get in. Now, I realize a lot of us right now, I know the formula's on the front side of the sheet, and a lot of us right now are busy trying to flip the sheet over to get the formula. And I get it. This is the only topic we're going to look at today, so well, Miss Golly, it's got to fit that formula, so let's do it. The issue is, though, if we don't get practice with that checklist, a question like this is going to be mixed in on your test. You have to be able to pick it out. You have to be able to pick it out. So let's do the checklist. Property 1, we need a fixed number of trials. Do we have that? Yeah, how many trials do we have? 6 of them, right? 6 people applying to medical school. 6 trials. Property number 2 says that we can only have 2 possible outcomes. They either get in or they don't. Property 2, check. Property 3 says our trials have to remain independent. So does the first person getting in or not affect the second? No. If it did, guys, you would have to be told that information. That's not something we are trying to read into a question. That if one person gets in, now that lowers the next person's chance. That's information we would have to be told. All right, so our trials are independent. And then the last one says probability of success has to remain the same for every trial. Is there anything in this question to indicate that that 90% is going to change from person to person? No. Again, don't read too much into things. Go with the information that you are given. So our checklist, we got all 4. Now I can say, yep, now I can use that formula for our binomial experiment. The pieces we need, N, capital X, P, and Q. You don't have to list these out first. It's something that helps my brain make less mistakes. I like to write down, here's all the variables I need to put a number in for, and then I pull those numbers from the question and I make my list. Then I substitute into the formula. I make less mistakes this way. I know for some of you are thinking, no, let's just grab the stuff from the formula and pop it, or from the question and pop it right in the formula. If that's how your brain works, great. I'm just trying to give you a suggestion to hopefully maybe lessen some mistakes, maybe. All right, so N is our number of trials. We have 6 graduates applying. How many successes do we want? 4. What's the probability that they do get in? 90%. So the probability they don't get in? 10%. Awesome. Okay. So now, probability for our accepted. I have 6 candidates. I'm going to choose 4 of them to get in. That's going to give me the number of ways that we can select 4 successes from our 6. Now we need that probability piece. Now we need that multiplication rule. So I have a 90% chance we're going to get in. And I need 4 of those. There's a 10% chance that they don't get in, and I'm going to have 2 of those. Please use the exponents instead of writing out 0.9 times 0.9 times 0.9 times 0.9 to show the 4. Then remember, we still need 6. We still need 6 total. Yes, absolutely use those calculator shortcuts. We should end up with, put it off this end, 0.098415. Now, that's not a terrible decimal to write the exact out. 6 decimal places isn't too bad. If you really feel the need to round, I know yesterday we talked about rounding to 1 more decimal place than our outcomes. That was for mean, variance, and standard deviation. This is a probability. Probability, we go 3 decimal places. So I know now we have to kind of think about those different rounding rules. The stuff we talked about yesterday, that applies to mean, variance, and standard deviation. Today what we're talking about, we're back to probability. And that's 3 decimal places, so just be careful with that piece. Let's take a look at 1 more of these, and then we'll take a look at the mean, variance, and standard deviation for this particular distribution. The reason I want to do 1 more example is because I want to make sure I touch back on some of that wording that I think some of us are not quite there yet from last chapter. So let's take a look. We have a shipment of 100 tires from the Apex Tire Corporation. It is known to contain 20 defective tires. 5 tires are selected at random, and each tire is replaced before the next tire is selected. What's the probability of getting at most 1 defective tire? So, let's do our checklist first though. I realize you guys are like, oh cool, I know how to use that formula now. I'm just going to start putting things in. Checklist first. Why do we get to use the formula on this question? Do we have a fixed number of trials? Yes. How many are we selecting? 5. 5 tires are selected. We're selecting 5. Fixed number of trials, we have 5. Do we have just 2 outcomes? Yes. It's defective, or it's not. There's nothing in between, defective or not. The last two properties, they always seem to really blend together for me. What's the one key word that helps me ensure my trials are independent and that my probability of success remains the same for every trial? What's the one word? Replaced. Replaced. If that tire, that first tire doesn't get replaced before we pick out our second, our trials are no longer independent. My probability of success has now changed also. So if that word replaced isn't there, properties 3 and 4 do not get checked. So this would not work. All the boxes are checked. So I'm going to write down N, X, P, and Q. Number of trials we already talked about. We're going to select 5 tires. Oops, sorry guys. How many successes do we want though? At most 1. So less than or equal to 1. So 1 or less. So 0 or 1. I'm going to list both of them there for my X's because we do need both. Now here's the tough part. Here's the big reason why I selected this example. What's considered a success? The defective tire is considered a success. That's what I'm looking for. Defective tire is what I'm trying to find the probability of. Now, from the company's point of view, is a defective tire a success? No. But for our binomial experiment, when we want to find the probability of at most 1 defective tire, the defective tire is our success. So the probability we get a defective is 20 out of the 100. Go ahead and simplify it down to 1/5 or to 0.2. Only use decimals though for P and Q if you don't have to round them. 1/5 works out really nice to 0.2. And then that means Q then would be our 8/10, 80%, however you want to look at that piece. All right, so we have the probability at most 1 defective is what we want to do. So we have to consider, we look over at our X and we need 0 defective. We also have to consider 1 defective. We need both of those things because we want at most 1, which means 0 or 1. All right, so we know all of our conditions have been met. We can go ahead and use our formula. We have 5 tires. I'm choosing 0 of them to be defective. The probability of being defective, which is considered a success, is our 20%. I don't want any of those. Probability we don't get a defective tire is our 80%, and I still need 5 of those. That's the piece we can't forget. That's where some of us got tripped up with our combinations and permutations on the Chapter 4 test. If we were selecting 8 students, and maybe you're trying to find that none of them were female, you guys would put that there were 0 females, but then you forgot about that we still need 8 students. So we are still selecting 5 tires, we just don't want any defective. Then we have 1 defective. There's 5 defectives, we're going to choose one of them. 20% chance we're defective, we want one of those. 80% chance we're not defective, we need 4 of those. I still need the same total number of trials no matter what. 0 defective and 1 defective. What are we going to do with those 2 situations? Add them together. Add them together. So go ahead and take a minute. Do a little computation in the calculator here. Go ahead and try it out. I'm going to go ahead and put up here the exact that I got. 73728. Again, if you wanted to round that, I'm okay either way. If you wanted to round it, remember you're going 3 decimal places. The other phrase I want to make sure we revisited while looking at the probabilities is that at least phrase. A lot of you on Chapter 4 tests, you really grabbed hold of the idea of using the complement. And others of us showed like, yeah, Miss Golly, I'm getting there. I got that 1 minus thing. I'm just not real sure how to find that probability that goes with it. So let's take a look. Our situation still stays the same. But now we're going to have at least 1. So if we talk about at least 1, we could realistically, at least 1 means 1 or more. So we could have 1, 2, 3, 4, or 5. Realistically, if you wanted to take the time, you could do the setup for, this is 1 defective up here. And then you have to do the same kind of setup for 2 defectives and 3 not defective. You have to do the same type of setup for 3 defective and 2 are not. And then 4 defective, 1 not, 5 defective, none aren't. You could set up all 5 of those and add them all together if you'd like. Or we can use the complement and make it a lot shorter and simpler. So if at least means 1, 2, 3, 4, or 5, what's the only case we didn't consider? 0. So 1 minus the complement, which would be 0 defective. And very conveniently, we already found that setup up here. So 1 minus, there's 5 we're choosing. We don't want any defective. 20% chance they're defective. 80% chance they're not. The exact answer for this. And then if you wanted to round, you're going to go to 3 decimal places if you're going to round. Either way is okay. And typically with these, they really don't usually get much beyond those 5 decimal place values. It's pretty common. But if they do start to get larger, that's okay. Just use 3 decimal places. Even with these, if you want to round to 3, that's totally fine as well. Totally fine. To finish up today, we're going to look at probably 3 of the easiest formulas we do for the entire course, to be very honest. They're pretty easy to use. They are the mean, variance, and standard deviation for our binomial distribution. So mean, variance, and standard deviation for our binomial distribution. There's going to be space for these for you guys in that bottom left-hand corner of your sheet. Bottom left-hand corner of your sheet. These are the formulas. I just left space there. I didn't have them labeled on your sheet for you. To find the mean, we just take n times p. That's it. I know we're used to those variance formulas and those formulas for the mean being super complicated, like we got to do a bunch of multiplying and then a bunch of adding and squaring and all that kind of stuff that we've seen the last couple times with means and variances and standard deviations. These are as simple as they get for those 3. For your variance, it's just n times p times q. And then your standard deviation, just your little sigma Again, you're just taking the square root of the variance. That relationship hasn't changed, nor will it. The one thing, make sure you practice when you're working on your assignments, make sure you practice working with your labels. I will expect that on your test, if I ask you for the mean, that you're giving me the appropriate label, or the variance or the standard deviation. So even though when you do your practice problems on these, you might not show much work, if any, practice with the label. Make sure you've got the labels down, okay? Make sure you've got your labels. So let's go ahead, let's finish up just by trying out these formulas a couple times, and then we'll get you guys a little bit of time to work today. All right, so we have a die being rolled 600 times. Find the mean and standard deviation of the number of ones that show on that, how many times ones will show when you roll the die. So we want to find the mean. So to find the mean, we need n, we need p. I'm just doing this for spacing, guys. There we go. And q. Again, take it or leave it. If you don't like listing these things out, you don't have to. If you just want to try to pull the numbers right from the question and put them in the formula, you can. But I feel like sometimes that's when I see mistakes happen. At least for myself, I know. All right, so total number of trials. We're going to roll the die 600 times. Probability of success. How many ones do we have on a die? Just one. How many total numbers? 6. So we're looking for ones, so p is going to be 1/6. That one has to stay a fraction. The decimal ends up being repeating, so that's really tough to enter back into a calculator. And so then q is going to be 5/6. The mean, again, practice writing that mu, just so you get that symbol in your brain. The formulas, you guys will get that formula sheet. They're going to be labeled, just like we saw on the last slide. Make sure you're using those labels. All right, and mu is just n times p. So if we're rolling a die 600 times, on average, we would expect to see a 1 100 times. Standard deviation, that's our little sigma, not squared. We're going to have n times p times q, and then we can't forget the square root. If we don't take the square root, we have variance. If we take the square root, we have standard deviation. So we get approximately, now I know some of you are thinking, rounding rules, Miss Galley, what is this one again? We go to one more decimal place value than what our outcomes would be. Our outcomes in this case, we're rolling a single die, so our outcomes would be the numbers 1 through 6. So if I go one more decimal place value, I'm going to go to the tenths. One final example working with our binomial distribution. We have a large online department store, finds, I left a lot of S's out in this, I'm noticing. A large online department store finds that approximately 17% of all purchases are returned for credit. If the store sells 100,000 different items this year, about how many items will be returned? We just want to find the standard deviation. Here's where we have to be careful. And again, sometimes it takes a little bit to kind of wrap our brains around the idea of that success versus failure. In the eyes of this store, a returned item, would it be a success or failure? In the eyes of the store, it'd be a failure. For the probability piece, for the standard deviation we're trying to find, the return is considered a success. That's where we have to be careful with that idea of success versus failure. In the real world, a returned item for a store is a failure. For our situation that we're looking at here for this binomial experiment, a return is a success. So we have to be careful. We have to try to separate that success failure reality versus success failure dealing with our binomial distribution. All right, so we had 100,000 packages. The probability of success is 17%. We just want standard deviation. So we do need that square root piece in there. So just be very careful, again, that idea of success versus failure on this. We have to be very careful. And also, be careful as well, if you're given a percent or a specific probability, don't automatically assume that that's going to be your success percent. Make sure you read the question carefully. This question could have just as easily have read, how many items will not be returned? And then our probability of success is 83%. So just be careful with that piece. Your assignment is in that bottom right-hand corner of your sheet. If you want to, and maybe with just the time you have left today, maybe you take a look at those calculator steps. It is a nice shortcut. The steps in your textbook on page 286 are great. They do a great job of walking you through. So if you want to play around with that a little bit, even maybe just with the examples we did today, or if you want to dig into those first few questions and maybe look at the shortcut, you can. I'm more than happy to help you with it. It's not something you have to do, but it is available to you. I know some of you really like using the calculator shortcuts, and others of you like, nope, I'm good with the formula. It's going to be on the card for me. That's what I want to do. So it's up to you if you want to maybe check those out.